liquid and gas phase. So if something is in liquid and entropy has to increase, so it should become gas. Okay, of course. If something is in solid, if it will become liquid, entropy will increase, of course. Right? This is the direction to increase the entropy. Just see, in metallurgical point of view, if solid will be there, we consider entropy is minimum or entropy does not exist. In a bigger term, I am talking about. In a bigger term, entropy is very minimum if solid will be there. But once gas phase is involved or once liquid phase will be involved, entropy will be there. That means in that system, entropy is sufficient. If gas will be more, entropy is more higher. Right? So this is direction. See, this is very interesting. Why? Because we start with 1 mole of gas, but it is becoming 2 moles. So that means in the reactant side, we have less number of moles of gas phase, but in the right side, we have more number of moles of gas phase. That means what is happening to the entropy here? Increasing. That means entropy basically depends upon liquid and gas phase. First I told. If the number of moles of gas phase is increasing, that means entropy is increasing. So this reaction is happening. Why? Because entropy is increasing. Very interesting. Oh yeah. Okay. Actually, that part is also there in your syllabus. I'll tell you in coming lectures. This is not the right time to discuss. Okay. See, basically, whenever you burn anything, let me give a simple example. You take a piece of paper. Piece of paper means what is that? Hydrocarbon, carbon and hydrogen bonds will be there. The moment you burn it, basically CO2 forms. And if hydrogen will be there, it will form H2O. Okay. You understand my point? Basically, it is carbon means it will form CO2 normal. But you take same piece of paper, you provide lot of carbon during that, and you take the material to very high temperature, around above 950 degrees centigrade. So what will happen? You will not get a product of CO2, but you will get a product of carbon monoxide. So actually it talks about stability of a particular product. So stability of a particular product depends upon temperature now. And other condition, carbon is available. See, let me give you an example. If you are getting a step, let me give you an example. Suppose there will be carbon dioxide is forming. Let carbon dioxide forms when you burn something. But this carbon dioxide, if so, these are lot of coke, for example. See, so lot of coke is there. For example, coke means carbon is available. This is carbon, and this forms. Okay, this forms. Temperature is suppose 950 or above that. This is the temperature. Temperature is available, carbon is available, and you are forming carbon dioxide. Then what will happen? This carbon dioxide itself react with carbon to form carbon monoxide again. CO2 plus C will give you carbon monoxide. You can balance it. 2 oxygen carbon. 2 carbon. You understand my point? But this should be condition. But if you normally burn something, carbon is not available. Temperature is room temperature. Carbon dioxide always forms. In simple word, I can say a particular compound will form depending upon the stability of it, and stability will be decided by temperature of it. So stability, free energy, entropy all depends upon temperature. So that is temperature dependent thermodynamics parameters. Did you get my point? Or you people understood how carbon monoxide is forming? Your temperature is sufficient, high, and carbon is also available. Even if carbon dioxide will form, it will react with carbon to again form carbon monoxide. It will not stay. So because carbon dioxide stability is gone now, carbon monoxide stability is increased, so it will stay. But if you will maintain a temperature of 200 degrees centigrade, so carbon dioxide will stay. It will form, it will stay. It will not form carbon monoxide. Is it clear? This is very important. You will get a question from this. Again, I am saying. So you can ask, so what A1 solid is also there, but as I told, solid don't play any role. Basically, it is stable already. It will not helpful for your entropy increase or decrease unless you melt it, or unless you make it gas completely. Right? You understood the point? So basically, if you check this reaction, in the reactant side you have less number of moles of gas, but in the right side you have more number of moles of gas. So if this reaction is happening, why? Because entropy is increasing in the right side direction. So more product will form because entropy is increasing towards right side. More number of gas phase is forming. But I told you, this is the concept, high temperature. And second law of thermodynamics also talks about the directionality of the process. So the reaction will move in this direction if temperature is high. Then on. Second law of thermodynamics talks about the directionality of a process, whether the reaction will happen or not. So this second law can also tell you. But condition of the temperature is involved. Is it clear or? You can write, instead of carbon monoxide, you can write CO2. Then tell me what happened to the entropy. Instead of carbon monoxide as a product, you write CO2 and just tell me, you all write and tell me. Carbon react with oxygen to form carbon dioxide. And tell me what happened to the entropy. Decrease. Decrease. How many of you are saying decrease? You write the reaction at least. C plus O2 gives rise to CO2. And tell me what happened to the entropy. Change. Entropy is increasing, decreasing, or what is happening? Constant. Of course, constant. Very good. Because you have to check the number of moles of gaseous phase available. Because liquid is not there, it will not hamper. But solid is there. Solid will not hamper. Only the mole of gas phase involved will hamper the entropy here. So in case of CO2, number of mole is gone. Oxygen, number of mole is gone. So reactant side have one number of mole of gas, right side have one number of mole of gas. So no entropy is changing here. Okay. But if you rise the temperature with time and you provide more carbon, CO start forming there. Is it fine? Okay, anyways, this part again I will discuss in Ellingham diagram. That is the main concept of this thermodynamics. That will help you during metal extraction. That part is called Ellingham diagram. We will discuss that. Because wherever you will go, they will ask this, what is Ellingham diagram? Videos are already available, so you can watch. Anyway, it is clear up to this? Okay, this is another example. Solid to liquid. You are melting something. Suppose you take a piece of iron, solid, you melt it. To do melting, what you have to do? You have to provide some heat energy. That means you are rising the temperature. Now, how you can say that the liquid will form? Tell me. Just correlate with entropy. Then you will understand. You have a piece of solid iron, right? You want to make it into liquid. So what do you have to do? You have to provide heat energy. You have to rise the temperature of that solid, right? So what happened to the entropy? Or how entropy is playing to make it liquid? Entropy increases when the moment the solid becomes liquid at high temperature. What happens to the entropy? Entropy is increasing. Why? Because solid has low entropy, but once it becomes molten state, liquid, more number of liquids are there, no? Entropy increases. So entropy depends upon temperature again. So in other words, I can say, just tell me, now you use your mind. What happened to the free energy of a solid iron below melting point? What happened to the liquid iron above melting point? I am talking about what happened to the free energy. Just raise your hand. Again I am asking, you have a solid piece of iron. What is the free energy of that solid iron below melting point? Below melting point means it will remain a solid. But the moment you take it into liquid, you have now liquid iron. So what is the free energy of liquid iron above melting point? Yeah, okay. Don't take, just raise your hand. You understood? Again I will ask. I am talking about free energy now. Free energy of the solid iron below melting point and free energy of liquid iron above melting point. Okay, 1, 2, 3, 4. Already I told you entropy and this free energy depends on temperature and they are opposite. Yeah, you were saying, let me answer. You were saying. No, I'm asking. You were saying. First tell me, I am talking about free energy. Free energy of the solid iron below melting point, what is that? It is less or more or what? Okay, you can answer. You are saying less. Okay. Less. No, my question, simple question was, what is the free energy of the solid iron below melting point? It is more or less? Less, very good. Less, very good. It will be less. That's why, that is the reason why always below melting point a solid phase always exists. That is the simple point. Some people ask this question, why a solid will be there below melting point? You simply say, because free energy is less. That means stability is more. So iron will remain a solid below melting point. But the moment you take the iron to above melting point, a liquid will start forming. Why? Because entropy is increased, your free energy will again reduces. That means above melting point, free energy of liquid is less. But free energy of solid will be just opposite, above melting point. So that means above melting point, free energy of liquid is less, but free energy of solid is more. So that is the reason why there is a change in phase. And if you remember in the earlier class I told you, phase transformation. One phase will become another phase, and that depends upon temperature and pressure also. Ma'am will teach you again in details. I also give an example if you remember. BCC iron become FCC iron at high temperature. BCC iron is one phase, and same iron also become FCC. The arrangement changes. The atomic arrangement changes. Why? That means in case of BCC iron, at room temperature, the free energy is less. But if you increase the temperature, the free energy will change. It wants to be more. But that's why iron will arrange in such a way that it can reduce its free energy. So it will arrange in FCC. So that at high temperature, when the iron atoms will arrange in FCC, the free energy will reduce. So it will stay as FCC. Do you understood or you are getting confused? You can ask me later if you are getting confused. Don't be scared to ask questions. We can discuss this. Is it fine up to this? Similarly, again interesting point. Mixing or alloying. As I told, basically we use alloys rather than pure metals in the day-to-day life. Whether it is your utensils to eat food, whether it is blade or whatever you are seeing, all are actually alloys basically, not pure metals. Anyways, I am giving an example. You take a liquid nickel and you take a liquid copper, right? Indivisible. Liquid nickel is there, liquid copper is there. But the moment you mix it, it will form a solution. Solution means you cannot identify where nickel is and where atoms of copper is. It will mix in such a way that it is a pure solution. Like you are mixing sugar into water. You cannot later find out where sugar atoms are. They will completely distribute everywhere uniform. You cannot find it, where the sugar atoms are. All are distributed. Same. You take molten liquid of nickel, molten liquid of copper. You mix them. It will become a solid solution. You solidify it. Finally, you get a solid solution. Solid solution means it is a solution of nickel and copper, but in solid state now. So my point here is, you have only single nickel, you have only single copper, but they are thermodynamically not stable. That means they have high free energy at that condition. But the moment you mix them and become solid, they become stable. They will stay for more interval of time. Nothing will happen to them. They will stay like that. Stability will increase. So that's why there is a concept called mixing or alloying. So can you tell me, if you measure the entropy of nickel and entropy of this copper, and you measure the entropy of the solution form, in which case entropy is more and less? Do you got my point? You have pure nickel, you measure the entropy. You have pure copper, you measure the entropy. And you measure the entropy of the solution which form by mixing nickel and copper. So in which case entropy is more or less or same or whatever. Okay. Entropy will be very good. That is the answer actually. Okay. So just imagine why this alloy is becoming stable. Why? Because entropy has increased. The moment you make a solution, entropy will increase. Right? Even if you maintain normal room temperature. See, I am talking about whenever you are measuring something, you have to keep everything constant, you have to change one variable. Then only you can measure something. If you are changing everything, you cannot compare it. So you take room temperature nickel, you take room temperature copper, you take room temperature alloy out of copper and nickel, and you measure the entropy. You will find out that entropy of the alloy is more, but entropy of copper is less, entropy of nickel will be less. So that's why the alloy form is more stable. The free energy has, that means, reduced due to formation of that alloy. Do you got the point? In other way, I can simply say free energy of this alloy is less. compared to the free energy of nickel, free energy of the copper. So in another way you can justify what is entropy. Entropy means if you are considering a system, how much configuration you can get. If you are getting more number of configuration, that means more entropy is there. If you are getting less number of configuration, less entropy is there. Configuration means here arrangement of atoms or arrangement of molecules. See, pure nickel, there will be particular arrangement. How will be the arrangement? Because pure nickel is FCC, phase 100 cubic. Okay. If you take pure copper, it is also FCC. Fine? Phase 100 cubic. But the moment you mix it, it may be FCC, it may be something else. I cannot say, I forgot exactly. But the moment. So that means the moment you are mixing, the copper atoms may be occupied by nickel, nickel atoms can be occupied by copper. So there is randomness now. You cannot find out where they are actually. The same corner atoms, maybe copper, can be nickel. But if you take pure nickel, corner atom is nickel, the phase 100 atoms are also nickel in FCC. If you take pure copper, corner atoms are copper, phase 100s are also copper. But the moment you mix them, maybe phase 100 will be copper, maybe phase 100 will be nickel, maybe corner atoms will be nickel, maybe corner atoms will be copper. So there is a randomness now. So you can have lot of configuration. Maybe sometimes it happens, corner atoms will be nickel, phase 100 will be copper only. Maybe it happens, corner atoms will be copper, phase 100 will be nickel. Maybe it will happen, corner atom will be nickel, corner atom will be copper. So lot of configuration can be possible now. Configuration means arrangement of atoms can be possible. So if more number of arrangement is possible, that means entropy is more. If you want to measure the entropy, that is called actually configurational entropy or entropy of mixing. We will discuss that in coming lectures, like after 10, 12 class we will discuss that. That is solution thermodynamics again. See why I am saying all this, so that you can correlate later. Otherwise if I will go with that, you will confuse what I am talking about. Entropy, but you don't know entropy. So finally I can conclude, we can have two types of entropy. One is thermal, because if we increase the temperature, entropy increases. If you decrease the temperature, entropy decreases. That is called thermal entropy. You take any material, you rise the temperature, entropy will increase. So that's why liquid is forming. No? Again you rise the temperature, gas will start forming. Again entropy is increasing. So entropy is temperature dependent, and that is called thermal entropy. But there is another concept. If you don't change the temperature, but you have lot of configuration available, entropy can be more. That is called configurational entropy. So one entropy is completely depend on temperature, that is called thermal entropy, and the entropy which depend upon number of configurations. Last one. If entropy depends upon configuration, arrangement of atoms in the system, that is called configurational entropy. So when you make a solution, configurational entropy will what? Increase or decrease? Increase or decrease? Increase. So in other way I simply say, if you have a pure nickel, what happens to the configurational entropy? Zero. There is no alternative options. All where same element is there. No configuration is possible now. All the same atoms now. All the same atom. So if you have a complete pure solid, configuration entropy is zero. You can change the temperature. You can take to high temperature, you can take to low, all the same. So configurational entropy is zero if it is a pure solid. Completely. Whether it is copper, whether it is nickel, whether it is iron, everything. But the moment you start forming alloys, alloy formation, it may be you can add carbon, like mild steel, just iron and carbon. You can add some stainless steel, you can add nickel and copper. To make a stainless steel, you add copper and nickel. Sorry, nickel and chromium, not copper. Chromium and nickel to the iron. Right? So that means I have three elements now, so more number of configuration is possible. So configuration entropy is. If only I have iron and chromium, if I have iron, see, let me give an example. If I have iron only, and I have iron plus chromium, and I have iron plus chromium plus nickel. Can you tell me what happened to the configurational entropy? in this direction? Increases. More number of configuration or more number of arrangement is possible, right? But here configuration entropy is 0. It increases, further increases. If I write and the alloying element, what will happen? Further configuration entropy will increase. So for a pure solid, similarly, last part I am talking about third law of thermodynamics. I will tell the definition and I will leave. So what is third law of thermodynamics is saying? Third law of thermodynamics is saying entropy is a temperature dependent phenomenon, which I have discussed right now. That means, do you know that what is the lowest temperature possible? Anybody remember this? What is the lowest temperature possible? Like this is the room temperature. You can take the temperature below room temperature, maybe minus. But what is the last temperature possible? Minus 270. 0 degree Kelvin. Technically, because we always represent the temperature either in Kelvin scale or maybe in centigrade scale, right? So I simply can say, if you take any material to 0 degree Kelvin, so what will happen to the entropy? Thermal entropy. It will become 0. Very good. This is the lowest temperature possible. So third law of thermodynamics is saying entropy is a temperature dependent phenomenon, and if you take the solid to that 0 degree Kelvin, entire entropy becomes 0. Well, means thermal entropy will become 0. You can write one statement. For a perfectly crystalline solid, thermal entropy is 0 at 0 degree Kelvin. For a perfectly crystalline solid, again you write, for a perfectly crystalline solid at 0 degree Kelvin, entropy is 0. So just imagine. This definition is considering both entropy now. Just read it again, you will understand. The term is perfectly crystalline. Perfectly crystalline means no impurities is there, no defects are there. So configuration entropy is also 0 at that condition. Because you cannot, because there is no impurities, no configuration is possible at all. So configuration entropy by default 0. And you have taken the material to 0 degree Kelvin, which is the lowest temperature possible. You cannot further reduce the temperature. That is the lowest temperature possible. So configuration entropy is 0, thermal entropy is 0. That means entire entropy becomes 0 at 0 degree Kelvin, but condition applied is it should be perfectly crystalline. But suppose you are taking a pure solid, but you are taking the material to 0 degree Kelvin. What happened to the configuration entropy and thermal entropy? It is a solid having some impurities maybe, and you are taking to 0 degree Kelvin. What will happen? Thermal entropy will be 0, but configuration entropy will be not 0. Because some impurities are there still. That is the second element now we can consider. Do you understand the point? So, first law, finally I am concluding. First law talks about conservation of energy. Second law talks about directionality of a spontaneous process. Unless I mean it is spontaneous, you cannot find the direction. Right? And also talks about entropy. And third law of thermodynamics will tell about the temperature dependence on entropy dependent on temperature. Okay? Is it fine? Any questions you have, you can ask me later. Okay, thank you.